Hey folks, so we got another problem. We have a church window consisting of a rectangle topped by a semicircle, and it's to have a perimeter of P. So we're just going to call the perimeter P. Find the radius of the semicircle if the area of the window is to be maximized. So we want the biggest window with a specific perimeter. So the perimeter can't be any bigger than a certain value. So what we want to do is draw a picture to represent this information. So you go back, it says window consists of a rectangle topped by a semicircle. So first let's draw a rectangle. And that's topped by a semicircle. So our church window is going to look similar to that. Now think about the values that's going to build this. First of all, if you have a semicircle, you're going to have a radius. So this distance we're going to call R. Now, and that's how you can measure both the area, okay, and the perimeter of the semicircle using that R value alone. And we'll write the formulas for that in a minute. But what about our rectangle? Okay, well, our width across the bottom is going to consist of two R's, right? If that rectangle is going to meet up with that semicircle, then this length down here is 2R. Now, the height, okay, or the width, whatever you want to call it, of the rectangle is not dependent on the width here. So that's just going to be, you could call it L, you could call it H. I'm just going to call it L. So I'm thinking about the length of the rectangle and the width of the rectangle. So W equals to 2R. Now, let's talk about the perimeter. Again, it's a fixed perimeter. So say the perimeter is, 1,000 inches or something like that. It's a fixed value, but we're just going to call it P. So P is equal to, now again, that's going to be the perimeter of the semicircle plus the perimeter of the rectangle, sort of. Let's talk about what that really means. So the perimeter of a semicircle. Now we know the perimeter of a circle is 2 pi r, right? But that's just half of it. So that's just going to be half of 2 pi r, which is just pi r, okay? Plus, okay, that's the perimeter of the semicircle plus the perimeter of the rectangle. Now, we're not really using the full perimeter of the rectangle, do you agree? Because we're not including this part, okay? So it's going to be an L here and an L here plus these two R's, okay? So it's going to be 2R plus 2L. Now that's the perimeter of the entire figure. We could simplify that just a little bit. I'm going to put it right out to the right here. P is equal to 1/2 times 2 pi r is pi r plus 2R plus 2L. Now we want to think about area. And by the way, this is your constraint equation or your secondary equation. It's the equation that's being limited by a certain value, which is just this fixed perimeter. Now let's talk about the area. Okay, how would you calculate the area? Well, think about it as two separate figures. For area, you have the area of the semicircle, and you're going to add that to the area of the rectangle. All right, so now you have area equals, the area of a full circle is pi r squared, so the area of a semicircle is going to be 1/2 pi r squared. And then the area of the rectangle is going to be, length times width is going to be 2R for the width times L for the length. Now this is the equation we're trying to maximize. Now what's our problem? Well, our problem is our equation we're trying to maximize has two different variables. The R varies and the L varies. So what we need to do is write this equation in terms of either just R or just L. And remember, that's what the constraint equation is for. So this equation right here, we want to use that to either solve for R or solve for L. It doesn't really matter which. And substitute into our maximize-minimize equation. So maybe right out beside here, let's solve this equation for either R or L. It really doesn't matter which one you solve it for. I tend to want to solve for the simpler one, the L right here. So to do that, what we might want to do is write R. You could factor out an R there. So that will give you P is equal to R times pi plus 2 plus 2L. I'm going to subtract the R times pi plus 2. So you got P minus R times pi plus 2. Because that's just a constant, that pi plus 2 is equal to 2L. And then to finally divide both sides by 2. So now I have L is equal to P minus R times pi plus 2, all divided by 2. That is my length. Okay, now what am I going to do with that length? I'm going to substitute it for L right here. That gives me an equation completely in terms of R. So now I have area is equal to 1/2 pi R squared plus 2R times P minus R times pi plus 2 over 2. Now what's really convenient is these 2's cancel, and I'm continuing to simplify my area equation, 1/2 pi R squared plus, I'm going to distribute that R inside, so that's PR minus R squared times pi plus 2. Now what am I going to do with that? I'm going to take the derivative of it, right? So now I have A primed is equal to, now I'm going to look at this as, now I have to R squareds. I could combine like terms there, but also I could just keep it separate and combine like terms later. So that is entirely up to you. Let's just go ahead and take the derivative now. So the 2 comes in front. 2 times 1/2 is 1, right? So that's just pi R when I take the derivative of the first term. Plus, now P, remember, is a constant. It is not a variable because it was a fixed value that the perimeter is constrained to. So the derivative of PR is just P. Alright, and then minus R squared times pi plus 2. Pi plus 2 is also just a constant. So we could write it in front of the R squared, but when I take the derivative of R squared, it's 2R. So minus 2, and I'm going to go ahead and put the pi plus 2 in front because it's a constant, times R. So there is my derivative. Now, again, I've got like terms here and here. I would probably do good to write that as subtracted. Okay, so I'm going to factor out the common R. That gives me A prime is equal to, then put the R in the back also. So it's going to be negative 2 times pi plus 2R. I didn't do that right. I just rewrote that. Plus pi R plus pi. There I just rearranged terms. Now I'm going to factor out that common R. Okay, so it's going to be negative 2 times pi plus 2 plus pi, all that, times R plus P. Now we can make that look much better. Now I'm going to go to the top of the page because I really want to simplify the derivative on this page, and then we can add another page to our work. So when I distribute this negative 2 inside, that's going to be A primed is equal to negative 2 pi minus 4 plus pi, all that's times R, plus P. That's simple as negative 2 pi plus pi is going to be negative 4 minus pi, or negative pi minus 4, R plus P. Finally, that is the first derivative. There was probably a much faster way to do that. If I would have combined like terms here, I could have got a better result, I think. Now, this looks like a crazy mess, but what we need to do is kind of recap what we did. Okay, so we wrote a formula for perimeter. And again, that's pi r plus 2r plus 2l. So again, the perimeter of the circumference plus the perimeter of this rectangle, not including the part in the middle. Then we found a formula for area, which was the area of the semicircle plus the area of the rectangle. the area of the semicircle was half of pi r squared. The area of the rectangle included 2r across the bottom plus L plus L. I'm sorry, 2r across the bottom times L, because we're taking area. Now my issue is I have r's and l's in my equation, so I went back into my constraint equation and solved for L, and that's where things got ugly right here, is because L is p minus r times pi plus 2 over 2. I substituted in for my L. I simplified that, probably not as much as I should have simplified it, but I simplified it. I took the derivative, and that's where we are. Now what I want to do is add another page to this, because you see how I've definitely run out of room, and I'm going to carry over our derivative. Anything else I need will come back to this particular page. Now that we have the derivative, what do we do with it? Well, we need to set it equal to 0, right? We're trying to find critical numbers. So when I set this equal to 0 and solve for r, the first thing I want to do is subtract the p over. So I have negative p is equal to negative 4 minus pi times r. I divide both sides by negative 4 minus pi. Now, y'all, that's just a number. All right, that cancels, so now I have r equals. So this is a critical number. Now, one thing I would like to do is factor this negative out of the denominator, which is going to cancel this negative here. So actually, p over 4 plus pi is our critical number. We only got one result. And remember, p is just a number. It could be 5 or it could be 1,000. All right, now, what am I supposed to do with that? Well, I'm supposed to plug that back into my original area equation, and that is going to maximize or minimize, depending on what we're looking for. We're looking for a maximize, right? So we're going to maximize the area of this particular figure. So when I plug that into my original area equation, here it is, area equals, I'll write it down, hold on. Now I wrote down our area equation, but I got to thinking when I wrote it down, there's something we need to do. We need to look to see what the problem asks for. So if we go back, so notice it says find the radius of the semicircle if the area of the window is to be maximum. It's trying to find the radius. Now you think about the endpoints of this situation. What's the smallest the radius could be? Well, the radius could be 0, but then you wouldn't have a window at all. So we know that one endpoint is not valid. That would be a minimum. The radius could also be equal to p, but then you wouldn't have any room left to draw your figure. Okay, so that's not valid. So we're pretty confident that the critical number that we found, which is this r is equal to p over 4 plus pi, is our maximized critical number, and it didn't ask for the area. So it is not necessary, and I certainly don't want to, it is not necessary to take that r value and plug it into that function to find out the area. All it wanted to know was the radius that would maximize the area of that window, and we found it. We're done with this problem. Yay! Okay, so this is the last example I want to go over with you. Hopefully this is a good variety of examples to help you set up your own optimization problems. So we have a cylindrical can. It's open at the top, and it's supposed to hold 500 centimeters cubed of liquid. So first of all, we have a cylinder. We'll try to draw that in a minute. It says find the height and the radius that minimize the amount of material needed to manufacture the can. So again, can you imagine two equations going on here? The constraint equation has to do with volume, right? We're constrained by this 500 centimeters cubed of liquid. So that's a volume. We'll have a volume calculation. And then find the height and radius to minimize the amount of material. So when you calculate the amount of material, you're talking about a surface area. So first of all, let's draw a can the best we can to kind of discuss what's going on here. So there's our can, okay? All right, now what's important about a can? Well, it's got a radius. What else is going on? It's got a height. Any other variables that you see? I think that'll do it, right? So we've got a radius and a height for our can. So let's talk about volume. How do you calculate the volume of a cylinder? Well, you have the circle, the area of the base times the height. A lot of three-dimensional figures, that's the formula. If you know the area of the base and then the height stays consistent all the way around or throughout the figure, then it's just going to be area of the base times the height. So what's the area of the base? We know the area is a circle. So we have volume is equal to pi r squared h. Okay, so our volume is 500 centimeters cubed, and that's going to equal to pi r squared h. That is our constraint equation. All right, on the other hand, surface area. Surface area is what we're trying to minimize. We want the least amount of material to create our can. Now we've got to figure out how to calculate the surface area of this can. Notice it said that the top is open, the bottom is not. So really you're going to have a circle for the bottom plus the sides. I say sides plural, really is like just one side because it's wrapped around. Think about what figure that's going to make when it wraps around. If you unwrapped it, it would certainly be just a rectangle, right? Where this is the height, but what's the length of that rectangle? Well, it would be like the circumference of a circle. It's got to wrap around and make one complete circle. So that circle is 2 pi r. So when you talk about surface area, I'm just going to call it S for surface area. I'm going to have the circle at the bottom, which is going to be pi r squared, because you're talking about an area, and this is also an area because we multiply length times height. So plus 2 pi r h. So this is the equation that we're trying to minimize. We've got to keep it to a volume of 500 centimeters cubed. All right, so what do? Well, our formula right now has r's and h's in it. We can't take the derivative like that. Well, we could, but we don't want to. We would like to write that all in terms of one variable, and we could do that because we have a constraint equation. So it's your choice whether you'd rather to solve this constraint equation for h or whether you'd rather solve it for r. I do think it would be a little easier to solve it for h. So that gives us h is equal to, I'm going to divide both sides by pi r squared. So it's 500 divided by pi r squared. And again, what am I going to do with that? I'm going to substitute the h down here with that value that came from this constraint equation. So now I have S is equal to pi r squared plus 2 pi r times my new h, which is 500 over pi r squared. Now, of course, I want to simplify that, so that's pi r squared. Now, this pi and this pi will cancel, and this r and one of those r's will cancel. I can multiply 2 times 500 to get 1,000 divided by r. And that would be my surface area, all in terms of r. Now, what do I have to do next? I have to take the derivative of my critical numbers. So I'm going to take the derivative of surface area, of course with respect to r, because that's the only variable I have remaining. So S prime is equal to, so I take the derivative of pi r squared, that's going to be 2 pi r. And I take the derivative of 1,000 over r. Now, what you might want to do is think about that as 1,000 times r to the negative 1. That's really what's going on there. So that's going to be, looking at this, negative 1,000 r to the negative 2 power. If I rewrite that in a simpler form, that's 2 pi r and then minus 1,000 over r squared. Now, what am I supposed to do? I'm supposed to find the critical numbers. Where do critical numbers happen? When the derivative is equal to 0 and where the derivative is undefined. Okay? Well, the derivative is equal to 0. Let's try that. So 0 equals 2 pi r minus 1,000 divided by r squared. Well, let's see. Let's add the 1,000 over r squared to the left. So 1,000 over r squared is equal to 2 pi r. Multiply both sides by r squared. So 1,000 is equal to 2 pi r to the third. I divide both sides by 2, and I get 500, and by pi, over pi is equal to r to the third. I take the cube root, so r is equal to the cubed root of 500 over pi. Okay, I'm going to circle that so I can find it later. Now, is this derivative undefined anywhere? Well, at r equals 0 is undefined. But you know what? At r equals 0, we don't have a can. So I'm not going to concern myself with that. If you don't have a radius or your radius is 0, then you don't have a can. Okay? You have nothing. So we're back to the fact that r is the cubed root of 500 over pi. Now I'm going to read my directions. It says find the height and the radius that minimize the amount of material needed. So we've got a radius. Okay, now that could be the maximum or that could be the minimum, but I do believe this is going to minimize our surface area. Okay, all right, now the next thing that we're going to do is find the height. Okay, now how do I find height? Right here. Okay, so we have height, change colors so it's easier to follow. Height is equal to 500 divided by pi, and then we have r, which is the cubed root of 500 over pi, and it's squared. Now that could probably be simplified some. To simplify that, you may want to deal with fractional exponents. I've got 500 over pi, okay? This is going to be times 500, and that's going to be to the 2/3 divided by pi to the 2/3. I think that's a little bit easier to deal with. Now, you could flip that, so that's going to equal, you know, I'm determined to get it all on one page. I'm flipping this fraction to multiply. It's 500 over pi times pi to the 2/3 over 500 to the 2/3. You with me? Now this pi and this pi to the 2/3, that's like 3/3 down there. So I'm going to subtract these two. The bigger one's on the bottom, so 3/3 minus 2/3 is pi to the 1/3 in the bottom. Similar thing happens here. This is 500 to the 3/3. This is 500 to the 2/3. The bigger one's on top. 3/3 minus 2/3 gives me 500 to the 1/3 here. Well, what does that give me? Well, 1/3 means you got a cube root of 500 over pi. Well, look. The height, the cube root of 500 over pi, is the same as the radius, the cube root of 500 over pi. Interesting, huh? So, a short recap of what you need to do for these problems is most of the time you come up with two equations. You have a constraint equation, which often is equal to a fixed value. Matter of fact, it's always equal to a fixed value, but sometimes you know the value, and sometimes, like the last problem, it's just a p, but a fixed value. And then you have the equation that you maximize or minimize. If the equation that you're maximizing or minimizing is in more than one variable, that's when you use the constraint equation to solve for one of those variables and substitute in the other. Then you have an equation in one variable, either all x's, all y's, all r's, all w's. You take the derivative, find critical numbers, and if you only get one critical number, that's most likely the result that you're looking for. But, you remember the problem we did with the wire, you still had to consider some endpoints. Okay, you had to consider if you're making just a circle only, or just a square only, or a square and a circle. And so we had to check those endpoints, whereas this one, we didn't even check the endpoints. What you really could consider for the endpoints here is if the radius was 0, that won't give you a figure. If the height is 0, that won't give you a figure. So we're talking this r equals cube root of 500 over pi is going to be the one to minimize your surface area. I hope that helps. These problems require you to really think through. Drawing a picture helps. Finding formulas to represent the information you have. But again, these are the general guidelines, and good luck to you, and let me know if you have questions.